What if an interstellar visitor, nicknamed 3i Atlas, came screaming into our solar system and didn't just pass by? It hit Earth? In this video, we'll walk through what that would look like at hypervelocity, from the first telescopic alert to the final planet-wide consequences. No hype, just clear, science-grounded what if. Imagine a visitor from far beyond our solar system, a dark speck drifting between the stars for millions of years, carrying the cold history of another sun. Astronomers label it with a code, but for us it's easier to say 3i Atlas. It isn't born from the same planetary nursery as Earth, Mars, or our familiar comets. It's a stranger, shaped by a different star's gravity and chemistry, and it doesn't share our neighbourhood's slow traffic rules. That alone makes it a wild card. When we call something interstellar, we mean it's not bound to the sun. It isn't looping around on a long, lazy comet path that repeats every few decades. It's on a one-way, open-ended track. It will rush in, curve a little as the sun tugs on it, and then keep going, never to return. That matters because it sets the stage for everything that follows. How fast it arrives, how early we can spot it, and how much energy it carries if it ever meets Earth. So what could 3i Atlas actually be? Picture three broad possibilities. First, an icy visitor, a few dozen to a few hundred meters across, think city block to small town in size, made of frozen water, carbon dioxide and dust, the kind of stuff we see in many comets. Second, a tougher, rock-rich body, more like a small asteroid, harder to break, and more likely to punch through the atmosphere. Third, a mixed rubble pile, a loosely held collection of fragments that looks solid from far away but comes apart under stress, behaving like a bag of gravel in a hurricane. Each of these options behaves differently on approach and during entry, and those differences decide whether we get a high-altitude airburst, a crater on land, or a wall of water at sea. Composition is the first clue. An icy body tends to shed material when it warms up, forming a faint tail and a fuzzy coma. That outgassing can act like tiny rockets, nudging its path in subtle ways and making prediction harder. A rockier body stays cleaner and more compact, which can make it dimmer and easier to miss until it's close. Density matters too. A dense, metal-rich rock carries more mass in a small package and is more likely to survive deep into the atmosphere. A fluffier, porous object can break apart higher up, spreading damage over a wide area rather than digging a single deep wound into the ground. Size is the second clue. Let's bracket a few scenarios that storytellers and scientists care about. Around 20 to 50 meters is the surprise class, big enough to blow out windows across a city or flatten forests if the angle and speed are unlucky. Around 100 to 300 meters is the regional class, an airburst or impact that could devastate a metropolitan area, or cause dangerous tsunamis if it hits water. Around 1 kilometer and above is where we start talking about continent-scale consequences, deep climate effects, and a long, painful recovery for the entire planet. We don't need exact numbers to understand the stakes. Doubling the size isn't just twice the problem. It can shift the event into a completely different category of damage. Speed is the third clue, and it's where an interstellar visitor like 3i Atlas stands out. Most near-Earth asteroids move fast, but still within the Sun's family pace. Interstellar objects tend to arrive hotter. Tens of kilometers per second relative to Earth is normal for them. That extra speed is not a detail, it's the headline. It boosts the punch dramatically. A smaller interstellar rock can hit like a much larger local one, simply because it's coming in so much faster. For a voiceover, here's the plain truth. Higher speed means a much bigger hit. Shape and structure are the fourth clue. A solid monolith acts like a sledgehammer. A lumpy, loosely bound pile tears itself apart as air piles up in front of it. Some bodies spin. Spin can stabilize flight like a football in the air, or it can help peel the object apart when the forces get intense. Surface cracks determine where it fractures. Voids inside it behave like hidden fault lines. Two objects with the same mass can deliver very different kinds of disasters simply because one is a compact bullet and the other is a fragile cluster. Now imagine the moment of discovery. A survey telescope in Hawaii or Chile picks up a faint dot gliding against the stars. A few hours later, another telescope catches it again. With 3 or 4 positions on the sky, astronomers start to fit a path. Very quickly, they notice it doesn't curve like a bound object. It's interstellar. The community gives it the nickname 3-Eye Atlas, and the race begins. Measure its brightness, estimate its size range, look for a tail, and watch how the sun's pull deflects it. That deflection tells us how heavy it might be. Any uneven spray of gas tells us about ices, and tiny changes from night to night hint at its spin, shape, and whether it's tumbling. All of those early clues help with one terrifying question. If 3-Eye Atlas is on a collision course, what exactly are we facing? If it's mostly ice and porous, the odds of a high-altitude breakup go up, which might mean a blinding flash, a rolling shockwave, and shattered glass across a wide area. If it's rocky and compact, the odds of reaching low altitude, or the ground, rise sharply. Over the ocean, both types can still be catastrophic, but in different ways. A compact impactor punches a deep, violent cavity in the sea that rebounds into powerful waves. A fragmenting one deposits energy over a broader patch of water, which changes the pattern and heights of the waves that radiate outward. Because 3-Eye Atlas is not from here, we also expect unfamiliar chemistry. Dust grains might be rich in exotic organics or metals in unusual ratios. That won't matter to the average person during the event, but it matters for prediction. Certain ices boil away sooner, changing how bright the object looks as it approaches. Certain minerals hold heat differently, which can change how the surface flakes and cracks. Even the colour of the coma can offer hints about what's inside, and those hints feed directly into the models that tell emergency managers how to prepare. Let's talk about angles. A shallow skimming entry spreads the damage along a long path and favours airbursts. A steep entry concentrates the blow and raises the chance of a crater. We don't control the angle. Nature rolls those dice. But once we measure it, we can tailor expectations. With a shallow approach over land, windows break in one city after another beneath the flight path. Sirens wail and cameras capture a blazing sun that shouldn't be there. With a steep approach, the story is shorter and crueler. A burst of daylight, a ground-heaving shock, and a wall of wind. There's also the question of how early we would know. A large 3-Eye Atlas might be found months out, giving time to refine the track with every dawn and dusk. A smaller one could slip past our attention until a week out or even days, especially if it approaches from the sunward side where telescopes can't look safely. That difference, months versus days, separates global planning from local scrambling. Months give us international briefings, rerouted flights and ships and targeted evacuations. Days give us shelter-in-place guidance, triage planning, and a lot of hoping the entry angle is kind. Finally, consider what makes 3-Eye Atlas feel so eerie. We're used to threats that come from the systems we know. Hurricanes, earthquakes, even ordinary comets. This is different. It doesn't belong to our sun. It's a messenger from another stellar family, carrying the scars of collisions and heat waves that happened light years away. If it were to strike, Earth would be meeting not just a rock, but the leftover history of another world. And that history arrives with all the speed and strangeness of the deep interstellar night. So as we set the stage for the rest of this video, hold these points in your mind. 3-Eye Atlas is a true outsider. Its speed is higher, its chemistry may be unfamiliar, and its structure could be anything from a frozen sponge to an iron hammer. Those traits decide how bright it becomes, when we find it, whether it breaks, and what kind of disaster it could deliver. In the next parts, we'll track how those traits translate into real-world consequences, first seconds, first hours, and the months that follow an impact no one on Earth would ever forget. Speed is the quiet villain in this whole story. When people picture a space rock, they think size first. How big is it? But with an interstellar visitor like 3I Atlas, the more decisive trait is how fast it's moving when it reaches us. Most near-Earth asteroids cruise on the cosmic highway at what feels like a brisk pace, but still within the Sun's neighbourhood rules. 3I Atlas doesn't play by those rules. It comes in on a one-time open-ended path with a head start from another star system, and by the time Earth crosses its lane, it's tearing along at tens of kilometres every second. For a voiceover, here's the simple punchline. The faster it is, the more damage a given mass can cause, so much so that a smaller, faster interstellar object can rival a much larger local one. Think about driving into a wall at walking speed versus highway speed. The car might look the same in both cases, but the outcome isn't even comparable. Space rocks work the same way. As speed goes up, the punch rises much faster than your gut expects. Double the speed and you don't just double the problem, you leap up by a lot. That's why a modest interstellar body can behave like a giant bully when it hits air. It's carrying an oversized budget of motion that has to be spent somewhere. Light, heat, shock waves, and, if it reaches the ground, a crater that writes its name into the landscape. That wild pace changes the story long before impact. It starts with discovery. Survey telescopes take short, repeated snapshots of the sky to catch faint moving dots. A slower object drifts a little between frames. A fast one streaks, smears, and sometimes hides in its own blur. That makes early measurement trickier and eats into warning time. Fewer clean data points mean a wider range of possible paths, and it takes longer to tighten those paths into a reliable forecast. With a fast mover, days matter. Each sunrise that passes without a clean track is a chunk of planning we don't get back. Now picture the moment 3I Atlas meets the atmosphere. Air can feel like nothing, but at these speeds, it's a brick wall made of gas. The air in front can't get out of the way fast enough. It piles up, compresses, and forms a shock front, an invisible needle-sharp bow wave where air is crushed and heated in an instant. Behind that front, the object's surface is blasted by a roaring incandescent wind. Rock or ice doesn't just warm up, it ablates. Layers vaporize, spool off, and spray away as a glowing plume. The brighter and hotter the flow, the more of the rock is sanded down in milliseconds. Speed decides where the real fight happens. Because the force of that air ram jumps quickly with speed, a very fast object can start to break apart higher than a slower one of the same strength. That sounds like good news, but it isn't that simple. Breaking apart early spreads the energy into a wider stretch of sky, which turns one bullet into a string of bombs. Each piece keeps racing forward in a fiery train, and the total energy budget, the one set by speed, still has to be spent. The result can be a high-altitude airburst that lights half the horizon and slams cities with shockwaves seconds later. If the body is unusually tough, dense metal, well-bonded stone, few cracks, then the higher speed can instead help it punch through to lower altitudes before it fails, making the blast much more violent near the ground, or even allowing a crater-forming strike. Same speed, different structure, very different outcome. Speed also shapes what we see and hear. The light show gets fierce as velocity climbs. More of the object's motion is converted into radiant energy, so the fireball grows larger and whiter, with a long persistent tail of ionized gas. You'll notice the colours, blue-white at the core, yellow and orange rolling outward, followed by a delay before the sound arrives. That delay stretches with distance. Flash first, then multiple sonic booms and a drawn-out, rippling thunder as the shock front drags across rooftops and hills. Windows don't care whether the blast came from a small fast visitor or a big slow one. They care about pressure jumps. Speed is very good at making those jumps. On the ground, speed decides the footprint. Blast waves decay with distance, but a faster impactor starts with a much larger budget, so the radius of damage grows. That's how a relatively compact, fast interstellar body can threaten an entire metro area, or, if large enough, an entire region. Thermal radiation rides along with the shock, and here again, speed is the multiplier. The flash can scorch skin, ignite dry brush, and start secondary fires that matter as much as the initial wind damage. In forests, that means crown fires. In cities, it means dozens of separate blazes that stretch responders thin. Over the ocean, speed is the difference between a splash and a slap that moves water like wet concrete. A very fast strike can carve a deep, violent cavity that collapses and pushes out waves with steep faces. But the details are subtle. Blast too high, and more energy stays in the air. Blast very low or hit the surface, and more energy couples into the water. Faster entries tend to favour stronger coupling near the surface, but fragmenting early can smear that coupling over a larger area, shaping the wave train differently. For coastal communities, the headline doesn't change. Higher speed raises run up risk and can expand the range of shorelines that see dangerous waves. Even the angle of approach starts to answer to speed. A shallow, skimming entry at extreme velocity can travel a long path through the atmosphere, dropping multiple bursts along a line and spreading damage over many towns. A steep, high-speed entry shortens that path and concentrates the blast in a tighter footprint, with higher peak pressures under the burst or at the crater rim if it gets that far. Emergency planners care deeply about this because it tells them whether to expect a ribbon of broken glass and roof damage across hundreds of kilometres or a compact zone of collapse and fire. For people asking, how does all of this change what we can do about it? Speed makes the human side harder too. Deflection missions work best with time. The faster 3i Atlas is moving, the less time we have from detection to arrival, and the smaller our windows to launch and intercept. Interceptors also have to meet that speed head-on, or from the side, which raises the technical challenge. Even if you get a spacecraft there, the physics of a fast, possibly fragile target can undermine the plan, hit it, and it may shatter into a spray of trouble rather than a single pushed rock. Civil defense options, evacuations, sheltering, hardening infrastructure become the realistic tools when the clock is short, and the speed is what makes the clock short. There's a quieter, unsettling point about speed that doesn't make flashy headlines but matters for forecasts. Small modelling errors get amplified when an object is moving very fast. A tiny uncertainty in where it is today becomes a big uncertainty in where it will be in a week. That's why, with a fast interstellar object, you'll see impact corridors on maps that are long and thin at first, then slowly shrink as fresh observations come in. It's not that we don't know what we're doing, it's that speed turns every small doubt into a long shadow until the data pile up. If you want a sense of scale, look at past atmospheric events we've recorded. Well-known airbursts moved at speeds common for long-period comets and still broke windows, injured people with flying glass, and lit the sky brighter than the sun. Now add another gear. 3i Atlas likely arrives faster than those, which means brighter flashes, stronger booms, and greater odds that even a modest body crosses the line from spectacle to disaster. That's the core of the speed problem. It quietly upgrades everything. It upgrades heat, it upgrades blast, it upgrades the size of the area that needs help. And yet, speed also gives us one advantage. It announces itself in the sky. A very fast object tends to be dramatically luminous in its final moments, which means the first warning, if we miss it in space, might still be a sky that turns to day for a heartbeat. That isn't the warning anyone wants, but it's the reality you plan for when the visitor is interstellar. For storytelling, keep it simple. When 3i Atlas races toward Earth, the number that rules the outcome is how fast it's coming. The same boulder at a lazy jog is tomorrow's curiosity. At a starshot sprint, it's the kind of moment that divides history into before and after. The story begins with a faint shifting point of light, so dim it barely rises above the noise in a camera's sensor. Survey telescopes sweep the sky in repeating patterns, night after night, making short exposures and comparing frames to find anything that moves against the fixed stars. Most nights, it's dust, satellites, and known asteroids. Then, in a run of images, a streak appears. Not a leisurely drift, but a sharp displacement from one exposure to the next, as if the dot is in a hurry. The software flags it. A human checks it. A provisional report is filed. In plain language, something new is here. Detection is a race against brightness and speed. If 3i Atlas is small or dark, it looks like a whisper on the sky. If it's approaching from the direction of the sun, it hides in daylight glare where ground telescopes can't look. Even from darker angles, the phase of sunlight on its surface, the way it's lit, can make it bright one week and stubbornly faint the next. A dusty, outgassing object may grow a fuzzy halo that helps us spot it earlier. A compact, rocky body can stay star-like and hard to pick out until it's much closer. And because an interstellar visitor tends to move faster than local objects, the images can show trailing, where the dot stretches into a tiny line. That line is proof of speed, but it also smears the light and makes the object harder to measure precisely. Once a telescope team snags 3 or 4 positions on the sky within a short window, the math engines wake up. Those positions form a tracklet, the first clue to a path. The Minor Planet Center receives the data and shares it so other observatories can chase the same target. Within hours, more telescopes try to recapture it. Different longitudes, different latitudes, different weather. Each successful follow-up adds a new bead to the string, turning a guess into a map. Very quickly, the path reveals something odd. It doesn't curve like a familiar comet. It's not circling the sun. It's on a one-time, open-ended route. That's the interstellar signature. From here, the question becomes time. How much warning do we have? That depends on size, reflectivity, and approach geometry. A large 3i Atlas seen against a dark sky could be discovered months before any potential encounter, buying space agencies and civil authorities precious time to plan. A smaller, darker body could slip past until it's much closer, discovered only a few weeks out, or, in a bad scenario, just days. Approaches from the sunward side are the worst. Even big objects can hide there until they swing into the evening sky, by which point the clock may be brutally short. In those first days, uncertainty is the enemy. With only a handful of detections, the forecast looks like a long, thin ribbon on a map. An impact corridor that might cross oceans and multiple continents, or miss Earth entirely. It's not that we're clueless, it's that the object is far away, moving fast, and tiny measurement errors multiply. Every new night of data tightens the ribbon. Parallel observing from different places adds parallax, like using both eyes to judge distance. If radar becomes possible, because the object gets close enough and the geometry cooperates, powerful radio dishes can ping it and listen for the echo. A good radar pass turns a blurry shadow into a near photograph of position and speed, shrinking uncertainties dramatically. But radar is not guaranteed. The timing has to be right, the object has to reflect well, and the facilities have to be available. If the window is missed, we rely on optical tracking alone. While the orbit hunters refine the path, a second team is trying to read the object's nature from its light. Does the brightness flicker every few minutes or hours? That suggests spin and shape, the kind of wobble you see from a lumpy rock tumbling through space. Does the colour skew towards certain wavelengths? That hints at ices or minerals on the surface. Is there a faint haze around it? That could mean jets of gas are pushing on it, slightly altering its track, which has to be folded into the predictions. Even small jets matter. Over weeks they can nudge 3i Atlas, enough to move the bullseye on Earth by hundreds of kilometres. Getting those subtleties right is how we avoid evacuating the wrong coastline or ignoring the right one. Public communication starts almost immediately, because rumours travel faster than objects. The first messages are cautious. A new interstellar object has been found. Early paths are being studied. The range of possibilities includes a near pass and, more rarely, a strike. People want a yes or no answer, but the honest answer early on is a sliding probability that changes with every observation. To make that digestible, agencies use simple risk scales that translate arcane numbers into clear categories like normal, meriting attention, and potentially dangerous. The key is transparency. Share the date of the next planned update. Explain why the impact corridor is long now and will narrow later. Show what data are still missing. When the public understands what uncertainty means, they're less likely to panic at every shift in the forecast. Behind the scenes, the cadence of observations becomes relentless. Wide-field survey telescopes sweep to reacquire the target on schedule. Fast, narrow-field instruments lock on for precise measurements. Southern and northern sights hand off through dusk and dawn. Amateur astronomers with serious gear join the effort, filling gaps when weather shuts down a major observatory. Each detection is time-stamped to the second, each coordinate cross-checked, each outlier questioned. Small systematic errors, like a slightly warped camera or a miscalibrated clock, can bend a predicted path by enough to matter for a city. Quality control is as important as quantity. With a month of warning for a mid-sized 3i atlas, you'd watch the corridor on maps shrink from broad stripes to a few hundred kilometers wide, then to a tight band. Airlines and shipping companies get early heads up to route around potential impact windows. Satellite operators weigh the chance of shock-induced drag and debris if the entry is steep. Emergency managers quietly draft evacuation options for coastal zones if an ocean strike looks likely. Hospitals and power utilities run tabletop exercises for a short, intense disruption. Schools and workplaces receive basic guidance. Be ready for official instructions. Know the simple sheltering steps if there's an airburst over land. Expect communication blackouts near the event. With only a week or two of warning, everything compresses. You still see the same path to clarity, nightly updates, narrowing bands, but there's less slack for mistakes. The questions shift from can we move it to who needs to be out and who needs to be in hardened shelter. Coastal towns might plan staged departures to avoid gridlock. Inland cities under a possible flight path prepare for window hazards, flying debris, and building alarms triggered by the shock. Authorities decide where to pre-position generators, water, medical supplies, and satellite phones. The watchwords become timing and trust. People need to know when to act, and they need to believe the message when it comes. Sometimes the first clear sign for the general public won't be a press conference, it will be the sky. If 3i Atlas is small and warning is short, the earliest universal alert could be an unexpected second sunrise near dawn or a brilliant streak at night. That's not good. But even then, simple instructions save lives. Don't stand at windows, get away from glass. If you see a bright flash, look away and cover. Count a beat, then expect a pressure wave that can knock you down and shatter panes. These are the same rules that protected people during past airbursts. They're easy to remember, and they cost nothing to practice. It's also worth understanding why false alarms sometimes happen early, and why that's not failure. It's caution. On day 1, the corridor might cross a city. On day 2, fresh data push it offshore. On day 3, the corridor clears Earth entirely. Each change reflects better knowledge, not indecision. The system is designed to err on the side of early notice, and then stand down gracefully when warranted. The alternative, silence until certainty, would rob communities of any chance to prepare. In the world of 3i Atlas, where speed and strangeness compressed the timeline, early tentative alerts are the responsible choice. If the path continues to point at Earth, the language in updates shifts from if to when and where. Times are given with margins, not single moments. Regions are named, not whole countries. For an expected airburst, altitude estimates guide advice about sheltering versus evacuation. For a likely ground impact, the focus tightens on downrange zones with the highest blast risk. Over the ocean, coastal warning systems translate impact location and depth into likely wave arrival times and heights. Maps go from broad pastel swaths to clear high-contrast polygons that tell mayors and governors exactly which neighbourhoods to move first. All the while, scientists keep trying to learn what they can about the body itself, because the nature of 3I Atlas will colour everything about the event. If the light curve suggests a fragile object, emergency managers prepare for a longer path of broken windows and scattered damage under a high-altitude chain of bursts. If it looks dense and compact, resources concentrate closer to the predicted endpoint, where shock and fire risk peak. If the glow hints at active jets, modelers allow for last-minute wiggles in the track, and authorities are warned to keep a small buffer in their evacuation lines until the final hours. In the best version of this story, discovery comes early, observation is steady, the corridor narrows cleanly, and a last-minute turn spares Earth. In the harder version, warning is short, the path stays stubbornly over land or a crowded coast, and the clock runs loud. Either way, detection and warning are a choreography. Find the dot, fit the path, tighten the map, and translate uncertainty into decisions regular people can follow. When the visitor is interstellar, when it's 3I Atlas, that choreography runs at double tempo. The tools are the same, the stakes are higher. The difference between chaos and coordination is how well we use the time we get, however little or much that is. When something from deep space meets our air at starshot speed, the atmosphere stops being empty sky and turns into an active opponent. Picture 3I Atlas slamming into a wall that happens to be made of a gas. Ahead of it, air can't move aside fast enough. It piles up, squeezes, and flashes into a superheated sheath. That sheath is the first battlefield. Rock or ice touches it and begins to ablate. Outer layers boil away, chips spool off, cracks race across the surface. Even a tough object starts to hiss and shed, not gently, but in explosive splinters that feed a growing incandescent wake. Whether 3I Atlas breaks apart high or low depends on a few simple traits: what it's made of, how it's built, how fast it's going, and the angle it takes into the atmosphere. An icy, porous body acts like a frozen sponge. It warms, steams, and crumbles early. A rocky monolith behaves like a sledgehammer, hot, bright, and less willing to yield. A rubble pile is the wild card. From far away it looks like one piece, but it's really a bag of boulders held together by their own faint gravity and a little dust acting like glue. Rubble piles tend to pancake under the enormous force of the onrushing air. They flatten, spread, and then shatter into a train of pieces, each piece brightening into its own fireball. That's how one large threat turns into a string of blasts along the same path. Speed is the quiet hand pushing all of this toward the extreme. The faster 3I Atlas arrives, the stronger the hammering from compressed air. That can make even a sturdy rock split earlier and higher than a slower cousin would. Higher breakup sounds comforting, but it isn't automatically safer. A high-altitude airburst pours its energy into the sky and sends a broad, rolling shockwave outward. The flash can light the night brighter than day. Seconds later, the pressure wave sweeps over towns and forests beneath the path. Windows blow in, doors slam, alarms trip. If the breakup happens lower, the shock is tighter and meaner, concentrated into a smaller footprint with higher peak pressures and more destructive winds. With 3I Atlas, which likely arrives faster than typical comets we've seen before, both versions get upgraded, brighter, louder, stronger. Entry angle steers the drama. A shallow, skimming path gives the object a long runway through dense air. It has more time to brake, more space to spread its fragments, and it paints a damage ribbon that can stretch across many hundreds of kilometres. People under that ribbon won't all feel the same thing. Close to the path, hard booms, sharp pressure jumps and showers of small debris. Farther away, a long growling rumble and a gentle rain of dust. A steep entry shortens the story and concentrates it. The blast piles up over a smaller area, and if any core survives the breakup, it pushes toward the ground still coherent, dangerous for cratering and for very intense near-surface shock. You can think of the breakup as a chain reaction. The outer shell fractures, fragments peel off and spin, exposing fresh faces. Each fresh face erodes faster than the last. If gases trapped inside find a pathway to escape, they vent like tiny rocket nozzles, twisting pieces and sometimes forcing them apart. The visible light curve, the way the fireball brightens and dims, often shows multiple peaks as sections fail in stages. To someone on the ground, this can look like a series of flares and booms marching across the sky. The light arrives first. The sound and the pressure come after, sometimes half a minute later for distant observers. That delay is why people get hurt by glass. They walk to a window to look, then the shock hits. Below the main burst, a rain of material begins what specialists call dark flight. Once the fragments slow enough, they stop glowing and simply fall like stones, guided by winds at different altitudes. That creates a strewn field, an elongated oval on the map where meteorites might land. In a small event, that means fist-sized rocks in a rural field. In a bigger one, it can mean a scatter of heavy fragments across many towns, enough to dent cars and knock holes in roofs. Most of the energy, though, was already spent higher up in light and shock. If 3I Atlas is unusually dense, imagine an iron-rich core with few cracks. The atmosphere's attempt to stop it becomes a brutal wrestling match. The fireball is whiter, the wake tighter, and the body holds together longer. There's a real chance it reaches very low altitudes before it gives up, or it may not give up at all. That's when cratering enters the picture. The instant a compact mass slams into the ground, it transfers energy into rock and soil, excavating a bowl, blasting ejecta in a radial pattern, and launching a ground-hugging shock front that races outward like a scythe of wind. Trees lie in rings. Structures fail on their weakest sides. Loose objects turn into missiles. Over water, the same rules meet a different canvas. A high-altitude airburst still hammers ships and coasts with pressure waves. But if breakup occurs low, or a compact core reaches the surface, water acts like a dense, yielding cushion. It caves in, then rebounds violently. The cavity collapse pushes out wave trains. Near the impact, those waves are steep and chaotic. As they travel, they sort themselves into broader, longer pulses that can run up on distant shores. A fragmenting entry spreads the coupling over a wider patch of sea, which can change the exact shape of the wave field. But the takeaway is simple. Lower, stronger coupling puts more energy into the water and raises coastal risk. The atmosphere itself becomes part of the show in ways people don't expect. The ionized trail, the electrically charged channel left in the wake, can briefly disturb radio communications along the path, like a moving bruise in the sky's ability to carry signals. The shock waves can bounce between layers of the atmosphere and the ground, making rolling booms that last far longer than the flash. High, thin clouds downrange can ripple as those waves pass, like a pond responding to a distant splash. Pilots may report turbulence in otherwise calm air. Weather radars sometimes see the debris and vapour, painting eerie, comet-like streaks on their screens. Small details change big outcomes. Surface cracks decide where the first major piece breaks off. Spin can either stabilise flight or help tear the object apart when the forces peak. A lopsided shape meets the air unevenly, and that unevenness turns into torque, then into tumbling, then into more uneven heating, another feed into the fragmentation loop. Even the texture matters. A glassy crust will pop and shed plaques. A rubbly face crumbles and exposes fresh, cool interior that briefly resists before it too joins the plume. Because 3I Atlas is interstellar, unpredictable chemistry adds spice to the problem. Some ices soften and vent earlier than others. Some minerals hold together longer under intense heat. Dust grains with odd coatings can darken the surface, making it absorb heat faster at the very time when staying cool is survival. Any outgassing jets alter the path little by little. Modelers have to watch the coma, the fuzzy glow around the body, for hints about those jets, then nudge their predicted track accordingly. A tiny shift early can mean a different city sits under the ribbon later. For people on the ground, the experience of an airburst follows a pattern. A glare, as if the sun has switched on in the wrong place. Shadows flinch. Birds erupt from trees. Then a pause, the eerie, silent heart of it. And then the booms, sometimes one, sometimes many, layered together into a deep concussive roar that feels as much as it's heard. Loose doors slam, ceiling tiles drop, window glass bows, and if it fails, it sprays inward. Simple actions matter. Don't stand at the window, look away and cover your eyes during the flash. If you're outdoors, don't stare up. Crouch, cover your head, and wait for the pressure wave to pass. If the path is extremely shallow, there's a slim chance of a skip, where the object sheds mass, flares, and then limps back towards space, only to re-enter later along a slightly different lane. That's rare and more likely for smaller, tougher pieces, but it's worth mentioning because a long, shallow passage can create a chain of bright flares that confuse eyewitnesses. People in one town might swear there were multiple objects. In truth, it's one body failing in stages, or one body and a handful of sturdy survivors continuing downrange. When scientists reconstruct what happened after the fact, they read the atmosphere's diary. Seismometers pick up the thump of the shock as it couples into the ground. Infrasound stations, built to listen for faraway rumbles, trace the blast around the world. Satellite sensors catch the flash and measure its power. Weather radars map the drifting cloud of particles. From those clues, teams estimate the entry speed, the altitude of major bursts, and the likely strength and makeup of 3I Atlas. That backtracking isn't just forensic curiosity. It improves the playbook for the next time, sharpening expectations about when an object will break and what that means for people below. Put it all together, and the atmosphere is not just a passive blanket. It's a dynamic filter that decides whether 3I Atlas becomes a sky-wide flash and a rolling roar, a ground-sculpting crater, or a sea punch that sends waves racing. A fluffy, icy visitor tends to lose the fight high and smear its energy over a broad swath. A compact, dense intruder carries the fight low, where the shock turns brutal. A rubble pile dramatizes the in-between, unzipping into a fiery necklace across the sky. The same total energy can write very different stories depending on how and where the air forces surrender. And because an interstellar object arrives fast, the margins thin out. Breaks happen earlier, but the budget of energy is larger. The flash is brighter, the booms louder, and the area of concern wider than our instincts suggest. That's why planners care so much about the first measurements: speed, angle, brightness changes, hints of jets, any flicker that betrays a tumbling shape. Those clues tell us which atmosphere story we're about to live. High breakup and a long ribbon of damage, or a fierce, compact blow that tests the strength of buildings, bridges, and nerves. In every case, the sky is more than a backdrop. It's the stage, the actor, and the referee deciding how the encounter ends. The final moments begin with light. If 3I Atlas has the strength to stay coherent and reach the ground, the first thing anyone near the impact point notices is a flash so intense it throws razor-sharp shadows and bleaches colour from the world. For a heartbeat, it feels like standing too close to a blast furnace. Paint blisters, dry grass curls, exposed skin stings. That thermal pulse races outward faster than the sound, bathing rooftops and treetops before any wind arrives. Birds erupt from trees. Streetlights with light sensors may flick off as if dawn has come in the wrong direction. Milliseconds stack into seconds, and the ground strike itself unfolds in a sequence too fast for the human eye, but not too fast for the Earth to feel. The approaching body drives a shock ahead of it, and when it hits, the surface reacts like a thick, brittle liquid. Rock and soil flow aside under impossible pressure, excavating a growing bowl. The rim heaves upward as if the landscape is trying to inhale. A curtain of debris lifts in a continuous sheet around the pit, fine particles riding high at the top, heavier blocks lower and closer. In the centre, target rock compressed by the blow rebounds and rises briefly like a spring being let go. That central uplift is a telltale of big craters. It will slump later, but in these first seconds it looks like the ground trying to push back. Shock becomes motion. The blast front fans out along the surface, a wall of pressure followed by a scything, dust-loaded wind. It outruns cars, topples signs and strips leaves. Roof tiles go airborne. Windows fail on the side facing the impact, then on the far side as pressure oscillates. Doors slam and frames rack as buildings flex. Loose objects become missiles. The gust isn't a gentle shove. It's a hammer that comes in a pulse, fades, then comes again as reflections and terrain channel the wave. Valleys funnel it. Skyscraper canyons steer it. Bridges vibrate as if a giant plucked their cables. Inside the growing crater, rock at the impact point melts and even vaporizes. Some of that vapor condenses into glowing droplets that are hurled outward. Tiny glassy beads that will later rain down as the sky cools. Larger clusts, fist-sized, car-sized, sometimes house-sized, arc in ballistic paths and land as a ring of ejecta around the rim. The outer edge of that ring is made of flipped and shattered layers, the landscape turned inside out like a peeled carpet. The inner edge is chaotic, a jumble of boulders and melt fragments. Where the impact strikes layered sediments, the ejecta may carry long slabs that land like toppled dominoes. Where it hits hard bedrock, the fragments are more angular and dustier. At the same time, the shock couples into the crust and runs as a seismic pulse. Nearby, it feels like an earthquake that starts without warning and doesn't follow familiar patterns. The frequency mix is harsh, rattling everything from dishes to bridge bearings. Farther out, conventional seismic waves carry the story to instruments worldwide, which will later reconstruct the size and depth of the blow. In the first minute, though, the shaking serves mainly to dislodge the already weakened brick parapets, decorative facades, and old chimneys that the wind was about to claim anyway. Thermal effects and blast effects overlap and create secondary hazards. Dry brush lights. In neighbourhoods, small fires start where embers land in gutters stuffed with leaves, where curtains meet broken glass, where gas lines or tanks are compromised by the shock. Industrial zones are especially vulnerable. Storage tanks, pipelines, and chemical warehouses don't like sudden overpressure. Automatic valves help, but a cluster of failures can feed plumes that complicate evacuation. The first responders map now has two colours on it: wind damage bands and ignition clusters. The air itself keeps a memory. The fast-moving curtain of ejecta, mixed with vapour and ash-fine dust, behaves like a ground-hugging surge. It's heavier than the surrounding air and it flows outward along the surface, especially in low terrain. Think of it as a hot, dirty fog bank with muscle. Close in, it can knock down weak structures and sandblast surfaces. Farther out, it loses force but still reduces visibility to a few meters and makes breathing difficult without protection. This surge is worst over dry, fine-grained targets. Wet ground and dense vegetation sap its strength. Power and communications fail in patterns that mirror the blast. Overhead lines whip together and trip breakers upstream. Substations on the wrong side of a pressure wave can lose control buildings or fence lines. Cell towers bend or drop panels. Even when they stay up, overloaded networks choke as everyone tries to call at once. Fibre in the ground is tougher but not immune. Bridge crossings, shallow trenches and manhole vaults are weak points. Radios remain the backbone in the first minute, but even they can be scratchy as the ionized plume above refracts signals, and the environment roars with electrical noise. If 3i Atlas strikes near water on land, say a river delta or a lake shore, there's a hybrid scene. The crater still forms, but saturated ground flows and slumps more dramatically. Water surges into the new basin and boils along its hot margins, throwing up jets of steam. Mud flows ring the site and channels feeding the crater may reverse temporarily under the pressure gradient. Bridges over those channels are at risk not just from wind and shaking, but from scour and debris jams in the minutes that follow. Topography writes its own local rules. A mountain between a town and the crater can shield neighbourhoods on the lee side from the first blast, only for them to be hit seconds later by reflected waves that wrap around ridges. Canyons punch the shock ahead like a nozzle, turning corners into pressure traps. Urban grids offer wind tunnels down certain streets, while leaving others oddly calm, so damage can look patchy from block to block even at the same distance. In forests, the pattern is easier to read. Trees lie with their tops pointing away from the impact. Then, beyond a certain radius, stand singed but upright, their needles browned by the flash. Vehicles react in ways that aren't intuitive. A parked car facing the blast might have its front windows blown in, and its rear window blown out as pressure equalizes. Trucks with high profiles can tip. Trains are vulnerable to track distortion where the ground heaves unevenly near the shock's passage, and tank cars can become a special worry if yards sit within the inner damage ring. Aircraft on approach to nearby airports will encounter turbulence and pressure disturbances unlike any storm. If they haven't already been diverted, controllers will find themselves juggling a sudden need for go-arounds and reroutes with a communications net that's blinking in and out. Human perception is its own timeline. People nearest the site see the flash, feel the heat, and are knocked off their feet by the wind almost before they can move. A little farther out, there's a gap between the flash and the blast that allows a beat or two to act. Turn away, drop, cover your head. Farther still, the experience is eerie. Daylight blooms from the wrong direction, shadows snap, and then a long rolling thunder arrives that seems to come from everywhere at once, rattling windows and nerve endings alike. In all zones, eye injuries from looking directly at the fireball and cuts from flying glass are among the most common preventable harms. Inside the crater, the physics is still busy after the first seconds. Melt pools slosh and crust. Steep walls collapse in stair-step slides. Blocks the size of buses teeter and then join the talus. Fumaroles, vents, open where gases escape from hot, freshly broken rock. If groundwater is present, steam explosions pepper the floor. The chaotic interior will keep reshaping itself for hours, then days, and heavy afterrain or snowmelt later can trigger further collapses. Anyone approaching that rim in the immediate aftermath faces a landscape that looks solid, but behaves like a trapdoor. Downwind, the sky takes on a dirty, coppery cast. The high plume rises like a chimney and spreads into a vast anvil, while lower layers drift as a layered haze. Sunlight through this veil turns strange, dim at midday, orange at evening, with halos and arcs as light refracts through ice and dust. Fine particles settle out slowly, coating cars and rooftops in a gritty film. In some places it falls as small, glassy spherules that ping faintly on hard surfaces. Rain that follows within hours can carry suspended dust into storm drains, where it forms heavy slurries and clogs outfalls. One more task for crews already stretched thin. Hospitals feel the pattern within minutes, close in, trauma from collapse and debris, mid-range, lacerations, burns, and ear injuries from overpressure. Farther out, breathing complaints from dust and anxiety spikes. Triage tents pop up in parking lots because indoor spaces near the blast may be compromised by broken windows and dust infiltration. The simplest supplies, eye wash, bandages, clean water, battery lights, become precious. Clinics outside the main damage ring step up to handle the wave as larger centres focus on critical cases. In industrial corridors, automatic systems fight fires and close valves, but manual checks are still needed. Refineries, power plants, and data centres are built with hardening in mind, yet the combination of thermal pulse, shock, and power quality swings is a cruel test. Gas turbines may trip, steam plants may vent as safety systems act. Battery farms switch to island mode if they can, keeping pockets of the grid alive. Microgrids, hospitals, campuses, some neighbourhoods prove their worth in these first hours if they were designed with independent operation in mind. If the impact happens on snow or ice, the early seconds gain a new texture. The blast scours to bare ground. Snow lofts into a dense whiteout that then turns grey as dust mixes in. Avalanche slopes sitting on the edge of stability can release. Lake ice shatters in radial patterns, sending pressure waves under the surface that crack boathouse pilings and shake fish up in their winter water. In permafrost, the sudden heat and mechanical disturbance can thaw a surprising volume of ground, creating thermocust pits and slumps in the days after. Wildlife reacts like people, flight first, then confusion. Herds run in arcs away from the shock and then mill in the first quiet valley they find. Birds that were aloft at the moment of the flash may be stunned by the pressure wave and fall. Aquatic life in nearby rivers can suffer from sudden turbidity and temperature spikes as hot ejecta and dust hit the water. These aren't the headlines on day one, but they are part of the environmental ledger that responders and scientists will tally as the scene moves from rescue to recovery. All of this assumes a compact, stubborn 3-eye atlas that kept itself together long enough to strike. If a fragmenting version delivers a near-surface burst instead of a true crater, the first-second physics is different, but the feel on the ground can be just as harsh. The blast still comes, the wind still scythes, and the thermal pulse still ignites. The difference is in the footprint, a wider, more diffuse ring of damage, less large ballistic debris, more shattered glass over a longer corridor. For cities, that nuance matters less than the practical advice that rides with it. Duck away from windows at the flash, shelter from wind and debris, and be ready for secondary hazards like fires and downed lines. By the end of the first minute, the broad outlines are set. A crater or a burned-in footprint defines ground zero. Concentric belts of damage radiate outward, crush close in, heavy structural damage beyond, then widespread but survivable effects farther still. The sky carries a dark signature. Networks are fragmented. People are moving, calling, helping, searching. The raw physics has done its work. The next chapter belongs to human systems, how they were built, how they fail, and how quickly they can be stitched back together. But those brutal first seconds, flash, shock, wind, fall, decide the starting point for everything that follows when a fast interstellar intruder like 3-eye Atlas meets solid ground. Most of our planet is water, which means most cosmic strikes land there. If 3-eye Atlas meets the ocean, the show unfolds on a blue stage that can carry its violence far beyond the horizon. The first sign is the same as on land, a blinding flash and a glowing column rising from the surface. But instead of carving a crater in rock, the blow digs a deep, temporary hole in the sea. Water cannot get out of the way fast enough, so it's shoved downward and outward, forming a cavity with steep walls. A heartbeat later, gravity takes over. The walls collapse, slamming inward and upward. This is where waves are born. Close to the impact, the water behaves more like a heavy, mobile surface than a gentle fluid. The initial splash is not a cartoon fountain. It's a chaotic tower of spray, steam, and churned foam, ringed by a dark moat where the surface has been dragged down. In that ring, hot gases from vaporized rock and water feed an expanding bubble that pushes at the surface like a fist from below. Around it, a train of waves radiates outward in all directions. These near-field waves are steep, irregular, and extremely dangerous to ships or platforms within sight of the event. They can throw a vessel off its heading, roll it to extremes, or break over the bow with the weight of moving concrete. As the waves travel, they self-organize. The ugly knotted pattern near the impact stretches into a cleaner train of long, low hills and valleys. These are not wind waves with short, choppy crests. They are long-period waves, the kind that keep their shape across entire ocean basins. To the crew of a ship hundreds of kilometers away, The first sign may be a slow, deep rise and fall that feels wrong to the body, too smooth, too powerful, lasting minutes instead of seconds. Farther out still, the wave can be almost invisible in open water, a long-limbed flex of the sea that only instruments notice, until it meets a coastline and shows its teeth. The way a coastline responds is set by its shape and the seafloor beneath it. Gentle, wide continental shelves tend to lift the wave slowly as it approaches, transforming deep water energy into a steadily rising flood that may extend far inland. Steep shelves and deep, narrow canyons keep the wave low until the last moment, then yank it upright into a steeper wall that breaks higher. Bays and inlets can act like amplifiers. A wave entering a V-shaped bay may be compressed sideways, forced higher as the walls squeeze together. Harbours with a natural slosh period that matches the wave's rhythm can resonate, making water levels heave up and down for hours, damaging docks, slamming boats into pilings, and sweeping debris in violent surges even when the first run-up wasn't catastrophic. The first wave is not always the largest. People trained in coastal hazards know to fear the set, not just the opener. After the initial surge, water retreats, dragging boats, cars and loose structures seaward. Channels that are usually tranquil turn into fast reversing rivers. Then another wave arrives, sometimes taller, sometimes arriving from a slightly different angle, if it has bounced off distant coasts or underwater ridges. That back and forth can continue, decaying slowly as the ocean bleeds off the energy along shores and on the seafloor. For coastal towns, this means danger lasts much longer than the first impact headline. Hours can pass before the sea settles. If 3i Atlas breaks up just above the surface rather than punching directly into it, the energy couples into the water differently. A low air burst can force a large swath of sea downward at once, like a giant palm pressing flat. The push is shallower than a deep cavity collapse but spread wide, which changes the footprint of the resulting waves. The nearby sea may see fewer extreme peaks, but a broader area of dangerous surges. The exact pattern depends on how the fragments fall, how low the burst is, and what the seafloor looks like beneath. The rule of thumb is simple. Lower and more focused coupling means steeper, more violent local waves. Higher and more diffuse coupling means broader but slightly gentler surges that still travel frighteningly far. Ports and offshore infrastructure are special cases. Container terminals stack steel boxes several stories high. A strong surge can turn those stacks into sliding, battering rams. Refineries and tank farms along coasts face the double punch of inundation and impact debris. Subsea pipelines can be exposed or snapped, where fast currents scour away protective sediments. Offshore platforms are engineered for storms, but a long-period wave with an unfamiliar profile can excite motions they weren't tuned for, stressing risers and joints in odd ways. Wind farms may ride out the passage gracefully if their foundations are deep, and the wave height in deep water remains modest, but cabling and substations on land remain vulnerable if flooding follows the run-up. Fisheries and marine ecosystems experience both immediate and delayed effects. Near the impact, the water column becomes a blender of superheated steam, shocked fish, and torn plankton. Farther afield, the passing wave itself is not what harms life. It is the suspended silt, debris, and sudden changes in salinity and temperature, where coastal water is forced far inland and then ripped back to sea. Estuaries, the nurseries of the ocean, are at risk of being flushed with a heavy load of mud, fuel, and chemicals from land, smothering beds of eelgrass and oysters that stabilise shorelines and feed larger food webs. Coral reefs can be physically broken by strong local surges and later stressed by cloudy water that blocks light. For people on coasts, the human story starts with warning. If the impact point is known hours ahead, regional alert systems can convert the location into predicted arrival times for each segment of shoreline. Sirens, text alerts, and broadcast messages guide people to higher ground. The instruction is plain and repeats across languages. Go up, not out. Follow marked routes. Do not return after the first wave. evacuation works best when it is rehearsed, and some communities practice this as regularly as fire drills, where warning is short or zero because the object came out of the sun. The first cue may be the sea itself. A sudden, unnatural withdrawal of water, exposing rocks and fish on the seabed, is a deadly lure. People who chase it risk being caught by the returning surge. Public education that plants a simple reflex: if the sea pulls back fast, run uphill, saves lives when technology cannot. Ships at sea face a different set of choices. In deep water, a long-period wave often passes harmlessly beneath a vessel that is headed into it with good seamanship. In harbours and near shore, the same wave can become unmanageable. That's why, when there is time, large ships are sometimes ordered to leave port early and wait in deep water rather than ride out surges at a berth where mooring lines can snap and hulls can strike concrete. Small craft should never try to outrun a surge along the coast. Trailers and dry storage may be safer if there is time to move them. After the event, navigation becomes hazardous as floating debris fields form. Logs, dock pieces, containers, and jumbled wreckage that can hole a hull or foul a prop. Not all coasts are equal. Low-lying deltas with miles of flat land behind the beach allow surges to push far inland with relatively modest heights. Steep volcanic islands can see localized megawave effects in narrow valleys where the surge piles up dramatically. Man-made defences, seawalls, surge barriers, dunes can blunt the first edge, but they can also reflect energy in ways that create hotspots of damage on either side. Natural defences like mangrove forests, salt marshes, and healthy dune systems reduce run-up by roughening the flow and trapping debris. Communities that have restored these buffers often find the line of destruction begins farther seaward than it would have otherwise. Communication during and after the waves is as important as the physics. Power fails first along the shore. Cell networks follow as towers flood or lose backup power. Battery radios and satellite messengers become the lifeline for neighbourhoods that have moved uphill. Helicopters and drones help map stranded pockets where roads have been cut by scour or blocked by debris. Bridges are inspected before use. The combination of fast water and floating impacts can damage bearings and piers in ways that aren't obvious from above. Water treatment plants, which sit low for gravity flow, are particularly vulnerable. Boil water advisories and emergency distribution of clean water become critical within a day. The environmental aftermath carries an ocean's fingerprint. Salt spray and fine brine carried inland can burn crops and corrode infrastructure quickly. Cars that were briefly submerged or soaked in salty mist begin to fail in the days after, electrical systems turning unreliable as corrosion blooms. In buildings, the mix of salt, silt, and organic matter left behind is a cleanup challenge. It keeps wood wet, feeds mold, and eats at metal fasteners. Sediment maps change overnight. Sand is stripped from some beaches and dumped on others, cutting new inlets through barrier islands and plugging old ones. Harbours and river mouths may need urgent dredging to reopen commerce. Weather and climate feel subtler but real ripples. The impact column injects water vapour and aerosols high into the atmosphere, where they can seed strange halos and optical effects for days. If the strike was large enough, chemical reactions in the hot plume can produce compounds that, once spread, play into cloud formation and sunlight scattering. Over the open ocean, this matters less for people than for the planet's radiative balance in the weeks that follow. Over coastal regions, it can accentuate already disrupted weather, producing hazy skies and colourful sunsets that become the eerie backdrop to recovery work. Response on the water requires a different posture than on land. Search and rescue moves fast but cautiously, watching for secondary surges. Teams bring inflatable craft, throw lines, and pole through neighbourhoods where street signs have vanished. Hazardous materials teams patrol industrial waterfronts to contain spills that would otherwise spread along marshes and beaches. Wildlife responders look for oiled birds and stranded marine mammals. Fisheries managers set temporary closures to let ecosystems settle and to keep contaminated catch off tables. Port authorities do damage triage, soundings to find new shoals, sonar to locate wrecks, divers to check pilings, quick repairs to get at least one channel open for aid. If 3i Atlas were large enough to push not only water but also climate, the ocean strike could add to a global story. Sea spray driven high into the atmosphere carries salty particles that can act as nuclei for cloud droplets. Along with dust and sulfates lofted by the blast, these can dim sunlight modestly on regional to wider scales for a time. That dimming, combined with disruptions to shipping lanes and fisheries, can ripple into food markets. Most impacts will not reach that level, but the possibility exists for kilometre-class bodies. In that case, the ocean's role would be a double-edged sword. It spared land from immediate crater devastation but turned the sea into a global messenger of the event. The most important public lesson is behavioural, not technical. Water hides danger in motion that looks deceptively smooth. A long, low surge can carry the power to break walls and move buses. The lack of whitecaps does not mean safety. The first run-up is not the end. Curiosity at the shoreline is deadly. The right move is simple. When the alert sounds, go to high ground and stay there until officials say the hazard has passed. Communities that practice this muscle memory, post clear signage, and keep evacuation routes free of obstacles fare dramatically better. Finally, it's worth stressing how much the local seafloor shapes outcomes. Two towns on different coasts can be the same distance from the impact and experience very different days simply because one sits behind a wide, shallow shelf and the other drops into deep water immediately. That's why modern models use detailed bathymetry and coastline shape to turn a point in the ocean into community-specific guidance. Expected arrival times, estimated flood depths, streets likely to become rivers, and safe zones that truly are safe. The ocean is vast, but its response is intimate, written in the contours of each bay and beach. If 3i Atlas chooses water over land, the world still feels it. Ships, ports, and coasts take the first blows. Bays and river mouths carry the surge inland. The sea breathes in and out for hours, leaving a line of wrack and wreckage that tells the story in muddy layers. For many regions, this is the realistic scenario. Most impacts hit the ocean. Planning for that reality means respecting the power of long waves, restoring natural buffers, building smart where retreat isn't possible, and practicing the one action that saves the most lives: climb, wait, and don't hurry back. The sky is the stage on which the whole planet reacts. After the strike of 3i Atlas, the first thing the atmosphere does is carry the story to places that never saw the flash. The violent column at ground zero punches upward like a blowtorch, lofting dust, ash-fine rock, droplets of melted material and vaporized water high into the air. If the burst is powerful enough, much of that mixture crosses the weather boundary into the stratosphere, a dry, cold layer where particles can drift for months because rain can't easily wash them out. What goes that high matters most for climate. Close to the event, the air feels wrong immediately. The blast pressure waves roll outward and bounce between the ground and the sky, making long rumbling booms that can be heard hundreds of kilometers away. Radar paints strange streaks where falling debris and hot plumes reflect signals. Airliners are rerouted around a growing no-fly zone as controllers watch the mushrooming cloud on satellite images. For a while, sunlight near the site dims and reddens as the thickest dust hangs in the lower atmosphere. This is the local phase, hours to days, where breathing may sting, visibility drops, and ash-like grit settles on cars and crops. Then the global phase begins. High-altitude winds, which flow like rivers around the world, grab the top of the plume and smear it into long veils that wrap latitudes. In a week, sunset photos halfway around the planet start to look unusual. Pearl-coloured halos, coppery horizons, and lingering twilight that glows with a strange metallic sheen. These are the optics of tiny particles in the high air, scattering sunlight in new ways. For most people, that's the first gentle hint that something enormous happened far away. What the particles are made of decides how strong the planet's response will be. Dust and pulverized rock mostly dim sunlight by acting like a fine shade. They cool the surface a little while they linger, then fall out in weeks to months. Faster if they stay below the stratosphere where rain can reach them. Sulfates, the hazy droplets born when hot gases rich in sulfur meet water high up, are the real climate players. They're excellent at spreading thin and hanging on. A rich load of sulfates can drop global temperatures for more than a season, nudging weather patterns and shortening growing seasons. Soot from wildfires, ignited by the thermal pulse and spreading for days, adds a darker ingredient that absorbs sunlight and warms the air layer it sits in while shading the ground beneath. Over ice and snow, falling soot lowers reflectivity and can speed melting once the sky's clear, adding a long tail to the local effects. Over land, the chain reaction is simple to picture. Less sunlight reaching the surface means cooler days, especially in the first summer after a large event. Cooler air holds less moisture, which can shift where and how hard it rains. Some places become stormier as temperature contrasts sharpen. Others turn drier as clouds struggle to grow. Monsoon systems, those grand seasonal breaths that bring rain to billions, are sensitive to heat contrast between land and ocean. A high, hazy veil that cools continents more than seas can shove those belts north or south, or weaken them enough to matter for harvests. Over the ocean, the story is slower but stubborn. The sea stores heat like a battery. A dimmer sun for a year or two means the upper layers take in a little less energy. That can stiffen or slacken winds that drive currents, adjust upwelling zones where cold, nutrient-rich water feeds fisheries, and alter storm tracks. Tropical cyclone seasons can bend weaker or stronger, depending on how the balance of heat shifts between basins. None of this is tidy. The climate system is a network of pushes and pulls. But after a big injection of high-altitude haze, expect the storm map to look off for a while. Breathing the air becomes a public health issue mainly in the near to mid-term and mainly downwind of the densest plumes. Fine particles slip deep into lungs and irritate airways. Communities under the first passes of the cloud may see spikes in asthma and eye irritation, especially if wildfires were part of the story and the plume carries smoke. Farther away, the haze is a lot thinner, more a sunset painter than a health threat, but airports and airlines still have to watch ash advisories. Volcanic ash brings engines to a halt. Impact dust can be similar. Detours and cancellations ripple through logistics at exactly the moment supply lines are under stress from everything else. The chemistry of the sky shifts in small but important ways. The blast's heat forges compounds that don't usually form so quickly, and high-energy shocks can split nitrogen and oxygen apart, making reactive gases that later help build ozone-damaging molecules. After very large injections, parts of the stratosphere can lose some ozone for a time, altering how much ultraviolet light reaches the ground. The effect is uneven and usually temporary, but it's one more twist in a year that already feels strange. Rain becomes a conveyor belt for whatever the plume carries. Some of the dust and sulfates fall out attached to raindrops, making precipitation slightly more acidic for a while. Usually not enough to burn leaves, but enough to nudge lakes and soils in sensitive regions. Where the dust is rich in certain minerals, the fallout can even act as a fertilizer over oceans, seeding plankton blooms. That's a reminder that the Earth system is full of feedbacks. A dimmer sun can slow plant growth on land, but a spark of nutrients at sea can liven up a food web for a season. These are ripples on top of the headline: cooler, hazier, and less predictable weather for a time. Crops and food supply feel the pinch quickly because plants are calendars tied to light and temperature. In mid-latitudes, shorter, dimmer summers mean slower growth and later harvests. In high-latitude farms that already gamble with frost dates, a few extra cool snaps can knock yields. In tropical regions, monsoon shifts can drown one side of a valley while starving the other. If 3i Atlas were small, these stresses remain mostly regional and short-lived. Hard months, not hard years. If it were a kilometre-class strike with a thick stratosphere-filling haze, the planet would talk about an impact winter, a harsh, multi-season dimming that demands rationing emergency grain reserves and quick changes to what and where we plant. Wildfire smoke is the free agent in this drama. The initial thermal pulse can light forests and grasslands over a vast area, and the blast winds can drive those fires fast. Days of burning can send their own black plumes high, independent of the impact column. That smoke changes local daylight into an eerie orange and pushes air quality into the danger zone. It also adds to the high haze if the smoke is lofted by storm tops into the stratosphere. In a large event, the sky becomes a collage. Pale, sulfate veils at cruising altitude, dirty brown ribbons lower down, and surface-level smoke pools in valleys. Sunlight that makes it through this stack is weak and red, the kind of light that wilts solar panel output and cools rooftops while playing tricks with human mood. Satellites, our weather eyes, see all this, but they also suffer through it. Some sensors struggle to read the ground through heavy, multi-layered haze. Radio links can be a bit noisier for a while as the ionized wake from the event and the lingering charged particles in the upper atmosphere bend and absorb signals. Most systems cope fine, but during the first days, the very tools we rely on to forecast the fallout are catching their balance. Ground-based instruments pick up the slack. Sun photometers measure how much light the haze steals. LIDARs trace the heights of the layers. Infrasound networks listen to the atmosphere's long, low notes to back-calculate the burst power. Nature writes vivid, short-term scenes. Sundogs and halos decorate cold skies as tiny ice crystals form around aerosol seeds. Twilight stretches, with the upper sky glowing long after the sun is gone. Moonlight turns strange, wrapped in a pale ring. These displays are beautiful and unsettling, ornaments on a deeper shift that farmers, grid operators, and emergency planners must navigate. Timelines help frame expectations. Hours, local ashfall, poor air and darkness near the site. Days, regional haze, flight reroutes, first sunsets tinged odd around the world. Weeks, stratospheric veils established, cooler afternoons, rain belts wobbling, persistent optical effects at dawn and dusk. Months, if the injection was large, a measurable global cooldown, altered storm tracks, and shortages as harvests underperform. 1 to 2 years, slow clearing of the stratosphere as particles drift down, gradual return of sunlight, climate patterns snapping back. Though not always to exactly where they were, because ecosystems and human systems have changed in the meantime. Size is the master gear. A 3i Atlas that breaks high and small will make the sky loud and bright and then let it heal quickly. A mid-sized impact that injects a decent load into the stratosphere writes a 1 to 2 year chapter of cooler, hazier weather and bruised agriculture. A true giant, a kilometre-class body that ramps sulfates and soot into a thick global veil, would push us into a rare, history-defining cold spell with worldwide food pressure, energy demand spikes, and emergency shifts in trade. The Earth has lived through such veiled years after big volcanoes. An ocean or land strike of the right kind could do the same. What can be done while the sky's dim? People adapt fast when they must. Greenhouses extend growing seasons and shield crops from ash. Cold-tolerant varieties are sown where possible. Stored grain is released to even out shocks. Fishing fleets reposition as plankton maps change. Power planners lean on dispatchable sources when solar output sags under haze and dust. Public health pushes N95s and indoor air filters in the most affected regions so life can go on while the air clears. None of this erases the strain, but it turns a blow into a wrestle instead of a collapse. In the end, the atmosphere is both messenger and cushion. It spreads the impact's touch to every country in the form of odd light, cooler days, and unsettled weather. but it also absorbs a huge share of the energy that might otherwise have gone straight into the ground or sea. With 3I Atlas, which likely arrives faster than our usual visitors, the sky's response is amplified. Brighter flashes, taller plumes, and a higher chance that the haze reaches the levels where it can steer climate for a while. The planet will recover, winds will scrub the high air clean, and rains will rinse the low air clear. The question that fills the months between is how we manage food, energy, and health, while the sky wears the impact like a veil. Civilization is a web of tight couplings. Power feeds water, water feeds hospitals, hospitals keep workers healthy, workers keep power running. When a fast interstellar intruder like 3I Atlas hits, the first seconds belong to physics, but the next days belong to those couplings. The damage does not travel in a straight line. It cascades sideways through systems that depend on each other in ways most people never see. Electricity is usually the first domino. Close to the blast or along a coastal surge, substations fail from wind and debris, switchyards trip offline, and high voltage lines gallop or slap together. The grid tries to heal by rerouting, but a big sudden shock makes protective relays err on the side of shutting down. Pockets of power remain, microgrids at hospitals, campuses and some neighbourhoods, but large swaths go dark. Without power, water utilities can't pump or treat. Wastewater backs up. Cell towers burn through batteries and then go silent unless they were hardened with long-duration backup. Data centres ride their generators. Some switch to island mode if they can. The pattern of outage on the first day is irregular and frustrating. An intact cafe with lights across from a dark hospital. A neighbourhood with radios and fridges beside another boiling rainwater in pots. Transport stumbles next. Airports within the hazard region halt for inspections and debris removal. Nearby airspace fills with detours as controllers work around the no-fly zone and the haze. Seaports stop operations if berths or channels are compromised. Even if they're intact, the surge of incoming aid ships has to be choreographed around damaged cranes and confused currents. Highways clog with responders, evacuees, and the simply curious. Bridges need structural checks. A few will stay closed until engineers crawl under them, delaying everything behind those choke points. Rail yards suspend movement until tracks are surveyed for warping, washouts, or debris. The effect is non-linear. One closed bridge can add a day to logistics for an entire region. Food systems feel the shock in two ways. Locally through direct damage to crops, storage and cold chains. Globally through price spikes and trade friction. If the strike starts fires or pushes saltwater far inland, fields in the plume's shadow may brown or burn. Greenhouses crack, irrigation pumps stop. Cold storage warehouses lose power and race to move perishables. Supermarkets manage shelf psychology, keeping some items stocked and visible to avoid panic. Farther afield, if the sky dims or shipping detours multiply, commodity markets jump. Grain exporters hedge. Import-dependent countries dip into reserves sooner than planned. The world can feed itself through a regional disaster. It strains when a large event adds a year of bad light and colder, twitchier weather on top. Healthcare rides the same spreadsheet as power and water. In the inner ring, hospitals take structural hits and lose glazing. Emergency departments move into corridors and parking lots. In the mid-ring, injuries from glass and debris flood clinics. Supplies, saline, dressings, antibiotics, burn down quickly. Sterile technique competes with dust and intermittent water pressure. Dialysis centres and patients on powered home care need electricity that may not be there. Pharmacies ration common essentials. In the following weeks, a second wave arrives. Respiratory complaints from haze, stress-related illness, and mental health strain. If an ocean strike brings contamination, add skin infections and gastrointestinal disease from brackish, polluted water. The system can cope, but only if neighbouring regions backfill staff and supplies, and if communication lines stay open. Information is its own disaster lane. People do not wait quietly. they reach for explanation and instruction. In the first hours, rumour outruns fact. Old footage resurfaces, labelled as new. Fake evacuation notices circulate. Opportunists push miracle filters and bogus donation links. The communications team that does best is the one that posts early, posts often, and repeats the same simple truths across radio, TV, text alerts, and plain language websites that don't buckle under load. This zone, shelter in place. This zone, move uphill. Next update, top of the hour. Credibility is a resource. It's spent and earned with each message. Community leaders, pastors, teachers, local influencers become amplifiers if they were brought into briefings early and given shareable, accurate templates. Governance is stress-tested by timing and clarity. Emergency powers exist for moments like this, but they work only if they're used with a scalpel, not a club. Curfews may be needed to keep people out of damaged zones at night. Price-gouging law enforcement matters to calm fear. Roadblocks should be tied to a clear purpose, keeping lanes open for fire and medical, steering sightseers away from unstable structures, and lifted as soon as that purpose is met. Coordination between city, regional and national levels is the difference between stacked efforts and crossed wires. Internationally, offers of aid pour in. Customs and visa bottlenecks should be pre-cleared by standing agreements, so trained teams and critical gear wheels straight through. Money moves on its own clock. Even if markets are closed for a day, risk is repriced the moment they open. Insurance claims spike. Loss adjusters need safe access and a process that works when offices are rubble. Payouts help households and small businesses bridge the shock, but exclusions, flood here, quake there, acts of God in fine print, can turn anger toward institutions if not handled with transparent compassion and emergency backstops. Central banks consider liquidity support if the banking system comes under pressure from operational outages or a rush to cash. Card networks reroute around dead nodes. Mobile money fills gaps if cell coverage survives. Cash distribution becomes a logistics mission where digital stalls. Refuge takes many forms. In a land strike, people within the heavy damage belt move outward along every available corridor. Stadiums, schools and churches open with cots and charging stations. In an ocean strike, it's often coastal neighbourhoods climbing a few blocks uphill and staying there through multiple wave cycles. With a larger climate-tilting event, displacement can extend for seasons as harvests wobble and some areas become temporarily marginal. The terms matter. Evacuation implies quick return. Relocation implies months. Labels influence how people pack, whether they bring pets and documents, and what officials plan for, short-term shelter versus intermediate housing with schools and clinics attached. Education is both a casualty and a stabiliser. Schools are buildings and bus routes, but they are also daily rhythm and childcare. Reopening classes, even in tents with filtered air, lowers stress for families and frees adults to rebuild. Curricula bend to the moment. Basic hazard literacy, air quality, safety and coping skills sit alongside math and reading for a while. Teenagers often become effective volunteers when organised. Debris sorting, information runners, supply distribution, giving them agency and reducing risky freelancing. Industry divides into brittle and resilient. Just-in-time manufacturing stutters as a single supplier in a damaged port town stalls an assembly line an ocean away. Firms with second-source contracts and inventory buffers glide better. Companies learn quickly which assets matter most: a specialised machine, a rare mould, a database server. Protecting and duplicating those crown jewels becomes the lesson written in the post-mortem. Data resilience is tested right alongside physical resilience. Where cloud regions overlap well and offline backups were maintained, businesses reboot. Where a single data hall held the only copy of a decade of work, there is no restart. Culture and psychology colour every lane. The weeks after a disaster are a mix of solidarity and fray. Neighbourhoods self-organise, shared grills for thawing freezers, childcare swaps, nightly check-ins. At the same time, exhaustion and uncertainty breed short tempers, Leaders who acknowledge loss, communicate boundaries, and celebrate small wins help hold the social fabric. Faith communities, clubs, and sports teams matter more than their budgets suggest. They are trust networks that move goods and calm rumours. Public rituals, memorials thanks to responders, milestones and cleanup mark progress and make the long middle bearable. Security is more mundane than movies suggest. Looting tends to be localised and opportunistic, not waves of marauders. The bigger threats are scams, cargo theft on chaotic docks, and crimes of opportunity in dark neighbourhoods. A visible, fair police presence, community patrols, and well-lit aid distribution points do more than armoured vehicles. Cybersecurity, though, needs guarding. Phishing spikes as attackers mimic official alerts. Hospitals and utilities already under stress are tempting targets. Pre-arranged quiet hours for network patches and incident response pay off in days like these. Environmentally, the ledger fills with both wounds and openings. Wetlands and mangroves that survived blunt surges and protect inland neighbourhoods prove their worth in numbers. Burn scars left by the thermal pulse and fires become flood risks in the first heavy rains. Contaminated sediments in ports and river mouths demand careful dredging and disposal. Some places take the moment to step back, move a few blocks inland instead of building the same seawall higher, buy out the most exposed properties and turn them into parks or buffers. Disasters force choices that planning commissions struggle to make in quiet years. Internationally, the narrative depends on size. A regional strike brings the convoy of heavy-lift aircraft, hospital ships, and field kitchens we've seen after tsunamis and quakes. A surge of competence that saves lives and resets systems within weeks to months. A larger, climate-tilting strike extends the horizon. Grain treaties loosen. Energy exporters and importers rework flows. Humanitarian agencies pivot from short-term relief to multi-season food security and shelter, while keeping an eye on secondary hazards like disease in crowded camps and migration pressures along long borders. Technology both strains and shines. Drones map damage and find isolated households when roads are gone. Mesh networks pop up to carry text between neighbourhoods without towers. Open source maps update hourly with passable streets and working clinics. Satellites turn from glossy Earth posters into practical tools. Where are the lights back on? Where did the shoreline move? Which bridges are back? 3D printing fills temporary gaps for small parts. None of this replaces trucks full of water and people with shovels. It accelerates smart use of both. The longer the haze lingers, the more the cascade blends with the ordinary business of life. Supply chains reknit around missing links. Farmers shift to varieties. Cities add shutters and film to windows, relocate substations, and bury a few more lines. Households keep a small cache of respirators, water and chargers alongside winter coats. Insurance products change. Building codes change. School drills include bright flash, look away, count, cover. The kind of simple habit that saves eyes and skin even if warning is short. It's not that we learn to love the risk. We learn to live with it without living in fear. In every version of this story, the total damage is not just the crater, the surge, or the sky's veil. It's the way those physical blows propagate through the systems that feed, light, heal, and connect billions of people. 3i Atlas doesn't have to be a civilization ender to be a civilization tester. The test is this: how well we keep the dominoes from falling in long rows, by hardening the first pieces, by building buffers between them, and by rehearsing who does what when the table shakes. Stopping a space rock is mostly about time. If you have years, you can be clever. If you have months, you can be bold. If you have weeks or days, you stop talking about moving the object and start talking about moving people. With an interstellar visitor like 3i Atlas, the clock runs faster than we'd like, so the plan has two tracks: space missions if time allows, and civil defense if it doesn't. The first move is always knowledge. You cannot push what you don't understand. As soon as 3i Atlas is flagged as a potential problem, telescopes keep it under constant watch, to pin down its exact path and how it spins. If there is any chance of a long lead time, a small scout spacecraft is the smartest investment. Think of it as sending a camera and a taper measure ahead of the tow truck. The scout flashes past or rendezvous, snaps detailed images, tastes the dust, checks how hard the surface is, and, crucially, measures how a gentle nudge would translate into a change in course. That visit can make the difference between a clean, surgical push and a risky swing in the dark. When there's time to act in space, there are three main families of push to consider. The first is the straightforward shove, a kinetic impactor. That's a fast, heavy spacecraft that slams into the object at high speed to give it a small change in motion. On paper it sounds simple. In practice it demands precise navigation, a steady aim at a tiny moving target, and good guesses about how strong or weak the surface is. A dusty, loose surface behaves like a cushion that throws extra debris backward, which can amplify the push. A tough, blocky surface behaves like a rock, less debris, more of a clean bump. One trick here is redundancy. Instead of one big impactor, you can launch a small swarm to hedge against surprises. If one hits a soft patch, another might strike a harder one, and their nudges add up. The second family is the slow tug. A gravity tractor is the classic image. A sturdy spacecraft sidles up and flies next to the object for months, holding position with thrusters. The two masses attract each other ever so slightly, and the patient pull changes the object's course. This sounds like science fiction, but the physics is polite and reliable. The catch is time. You need a long runway to make a meaningful difference. A related slow push uses engines that thrust against the surface indirectly, ion beams or tiny rockets that blow material away without landing. Again, gentle but time-hungry. The third family is the harsh, fast option, a standoff nuclear burst to vaporize a thin layer of the surface. That flash of heat boils material off one side, and the recoil acts like a giant thruster. The spacecraft doesn't need to touch the object, it fires at a safe distance. Used above the surface, this approach aims to avoid shattering the target while still producing a strong push. It's the only technique with enough raw muscle to work even when time is short and the object is large or unusually tough. The risks are political, legal, and technical. You need international authorization, absolutely clean command and control, and confidence that the burst won't fragment a fragile rubble pile into a worse problem. Still, if 3i Atlas is on a collision course and the calendar is cruel, this is the option planners keep in the drawer for a reason. All of these space options get harder with an interstellar target. 3i Atlas is likely moving faster than our usual near-Earth asteroids, which means launch windows are tighter, intercept speeds are higher, and the time between discovery and encounter shrinks. That pushes mission design toward pre-built interceptors that can be pulled off the shelf, stacked quickly, and launched on whatever rockets are ready. It also favours rideshare strategies, using multiple launch vehicles to send smaller pieces that meet up in space, so no single delay kills the whole plan. Autonomous guidance becomes non-negotiable. At close range, the spacecraft must be able to lock on, dodge debris, and correct its aim without waiting for commands to crawl back and forth from Earth. A clean deflection plan usually pairs a push with a second spacecraft that watches from the side and measures the effect in real time. If the first nudge didn't move 3i Atlas enough, you retarget. If the nudge sent a plume of debris into a worrying path, you adjust. This feedback loop is how you keep a delicate operation from drifting off into wishful thinking. It's also why early investment in planetary defense, tested navigation, proven sensors, reliable propulsion, pays off wildly when the day comes. Now turn the clock forward to the grimmer timelines where space missions aren't possible. If warning is measured in weeks, not years, the priority shifts from pushing the rock to protecting people. The good news is that simple practice steps save a lot of lives, even in terrifying scenarios. The key is to tailor them to what 3i Atlas is likely to do. Airburst high, explode lower, hit land, or strike ocean. For airbursts over land, the biggest preventable injuries are from broken glass and falling debris. Public guidance must be plain and repeated everywhere. If you see a blinding flash, do not go to windows, turn away, cover your eyes, and get low. Seconds later, a pressure wave will hit. After the booms, expect secondary damage, sprinklers, alarms, and small fires. Cities can pre-stage a few simple upgrades that make a huge difference. Shatter-resistant film on big public windows, automatic door releases that prevent people from being trapped, backup lighting and PA systems in schools, hospitals, and transit hubs so instructions can be heard in the dark. For ground strikes, the response depends on distance from the predicted epicenter. Inside the inner belt, evacuation is right. Outside it, sheltering in solid buildings is often safer than gridlocked roads. The message should include clean, visual maps with zones that do not change unless new data truly demand it. That avoids whiplash and rumour-driven panic. Evacuation routes need traffic control, fuel caches, and breakdown services. Even a handful of stalled vehicles in the wrong spot can freeze a highway at the worst moment. Hospitals and clinics in the mid-belt should discharge stable patients early, expand capacity, and pre-position supplies that run out fast. Oxygen, antibiotics, eye wash, dressings, and portable power. For ocean impacts, coastal communities must act on a different rhythm. The right move is up, not out. Sirens, texts, and radio alerts need only a few words. Impact location, estimated arrival time, and go to high ground now. Practice, annual walkouts, clear signage, and routes without choke points turns that message into muscle memory. Ports can secure cranes, lower stacks of containers, and move hazardous materials to safer elevations if there is even an hour to spare. Large ships should leave harbours if time allows. Small boats should not try to race surges along the shore. After waves arrive, the hardest rule to follow is the one that matters most. Do not go back after the first surge. Sets can continue for hours. Information is its own form of shelter. In short warning scenarios, misinformation multiplies harm. The counter is relentless clarity from trusted voices. A single source of truth updated on the hour. Radio stations designated ahead of time. Community leaders and local influencers brought into the loop early with shareable translated scripts. If authorities don't fill the silence, rumours will. If authorities explain why a corridor is long on day 1 and narrow on day 3, people accept updates instead of calling them lies. Critical infrastructure can be hardened cheaply in ways that matter. Substations can add blast baffles and fire breaks. Cell towers can get longer life batteries and quick connects for mobile generators. Water plants can elevate control rooms and stock spare pumps. Clinics can keep portable HEPA units and respirators for smoke and dust days. Schools and shelters can store cots, chargers, radios, and basic medical kits. None of this requires knowing the date of 3i Atlas. It simply treats the impact threat as one more hazard on a list that already includes storms, quakes, and fires. One of the most effective mitigations costs little: drills. You cannot invent choreography in the moment. Cities that practice bright flash safety in schools, that run coastal evacuation walks, that test their radio nets and publish backup maps on paper. These cities lose fewer people to confusion. Families that keep a small kit, water, snacks, flashlights, batteries, a radio, copies of documents, bounce back faster. Businesses that mirror their most critical data across regions and rehearse, operating without cloud access, avoid the worst digital paralysis when networks blink. There is also the quiet work of choosing what not to rebuild where it will only break again. After an event, the urge to replace what was lost is strong. A smarter stance is to treat the scar as a map. If a neighbourhood sits in the inner blast ring or the deepest run-up zone, consider buying out the most exposed blocks and turning them into parks, dunes, or wetlands that will blunt the next hit. If a substation failed because it was low and close to the shore, move it inland or elevate it. If the sole highway out of a coastal town crosses a single vulnerable bridge, add a second route. These choices are political, but they are also mathematical in spirit. Every buffer you add shortens the chain of dominoes the next time. On the global level, mitigation means institutions ready to sprint. That includes launch-ready interceptors on the space side, and on the ground it includes pre-negotiated aid corridors, modular bridges and power units stacked in warehouses, and teams trained to set up water and communications in days. It means grain reserves in multiple countries, not just one, and agreements that let those stores move quickly without bureaucratic knots. It means a playbook for airlines and shipping to reroute around no-fly and no-sail zones without stranding essential goods. It means a habit of sharing data, orbital measurements, plume maps, wave models, openly and fast. Because 3i Atlas is a stranger, humility is part of mitigation. Assume the object could be tougher or softer than expected. Assume light curve hints can be wrong. Assume last-minute shifts are possible if jets of gas turn on. Space plans should build in margin with extra fuel, extra sensors and backup targets. Civil plans should keep a little slack in evacuation lines and refuge zones until the very last tracking update arrives. Flexibility is not indecision. It is how you steer between panic and overconfidence. There's a philosophical layer too. The tools we build for this threat, wide-field sky surveys, fast launch rockets, resilient grids, smarter coastal planning, pay off for other hazards. Telescopes that catch 3i Atlas early also catch smaller, local asteroids before they surprise us. Launchers kept warm for planetary defense help in other emergencies in space. Microgrids that keep hospitals bright during an airburst also keep them open during storms. Mangroves planted for surge protection, shelter fish, and cleanse water year-round. Preparedness is not a single-purpose expense, it's a multiplier. If you picture this all as a ladder, the first rungs are every day. Better surveys, faster data sharing, stronger windows, clearer drills. The middle rungs are choices. Pre-built interceptors, hardened infrastructure, diversified supply lines. The top rungs are rare but decisive. A scout probe on short notice, a kinetic nudge, or, if forced by the clock, a standoff burst that turns 3i Atlas a few minutes early so Earth isn't there when it passes. We don't need perfect certainty to climb. We need habits that make sense even in the many years when the sky's quiet, and the courage to move fast and together when it isn't. In the end, mitigation is not magic. It is a chain of practical moves that start with seeing the visitor early, and end with taking care of people if we can't move it in time. Interstellar or local, small or large, the verdict is the same. The earlier we know, the gentler the fix. And if the warning is short, the most powerful tools we have are clear instructions, practiced actions, and a culture that treats preparation as normal, not paranoid. That's what turns an impossible problem into a survivable one. The first quiet after the blast feels unreal. Sirens falter. The air still tastes like metal and smoke. In that hush, the work of years begins. The first day is about life, finding the living, stabilizing the injured, reuniting families, clearing a lane for ambulances and water trucks. Search and rescue teams move methodically, grid by grid, building by building, marking what's been checked and where to come back with heavier gear. Neighbours form bucket lines, pry doors and shout names into the dust. In coastal towns after an ocean strike, the search includes rooftops, tree lines, and the tangled edges of marshes where the surge left people stranded. Helicopters and small boats become lifelines. The most precious resource is organisation. Whiteboards, radios, runners, a few people who can turn the chaos into lists that get shorter by nightfall. Day 2 and 3 shift to stabilisation. Power returns in patches, first to hospitals, water plants and shelters. Temporary cell towers and satellite links light up the map. Distribution points for water, food and basic care open on predictable schedules. People find out what they need to know, where to charge a phone, where to get insulin, where to sleep if a home is gone or unsafe. Debris begins to move out of the streets, not randomly but with a plan, separating green waste, household rubble, and hazardous materials so the wrong pile doesn't foul the right one. Fires that smouldered overnight are doused. Damaged buildings are shored or cordoned. In the tsunami zones, silt is scraped out of the ground floors and pushed to staging areas for testing. The goal is to keep contaminated mud from being spread back into neighbourhoods. The first week draws a line between emergency and continuity. Schools become day shelters with activities and meals. That small normalcy steadies kids and gives caregivers hours to sort paperwork, meet inspectors, or help on cleanup crews. Pharmacies open under tents with emergency waivers. Clinics run mobile rounds to the hardest hit streets. Laundry stations appear near shelters, a small miracle that restores dignity fast. Religious spaces host quiet corners for grief. At community meetings, leaders speak plainly: what's open, what's closed, what's next, and what questions don't have answers yet. Honest, we don't know yet, builds more trust than confident fictions. Money becomes the hinge between surviving and rebuilding. Emergency cash grants reach households quickly through multiple channels: digital where networks work, paper where they don't. Insurance adjusters set up shop in gymnasiums, and the best of them adopt a triage of their own, fast-track clear claims, escalate complex ones, and translate the fine print into human terms. Small businesses get microloans and permit relief to reopen on sidewalks and in shared markets while their buildings are repaired. Rent relief and mortgage forbearance prevent a second wave of displacement. A predictable, published timeline for utility restoration and debris pickup helps shops place orders and hire back staff. The environmental recovery plan starts in parallel, not later. Rivers and harbours are tested daily. Booms corral fuel slicks. Teams inventory damaged tanks, labs and warehouses so the worst hazards are contained first. In forests and grasslands singed by the thermal pulse, crews cut fire breaks and remove widowmaker limbs before reopening trails. Where the surge-salted fields, agronomists map the burn and recommend which crops can tolerate a season of stress and which soils need fresh water flushing. Seed and tool banks distribute hardy varieties so farmers don't lose a planting window. Along the coast, dunes are replaced and anchored with fencing and grasses. Mangrove and marsh plantings begin while the memory is fresh and the community is motivated. These are not cosmetic fixes. They are living infrastructure that will blunt the next surge and trap debris before it can grind through neighbourhoods again. Public health moves from trauma to prevention. Air quality advisories continue as demolition raises dust. N95s are handed out where the haze lingers. Tetanus shots and wound care clinics pop up for cleanup crews. Mental health care steps out of offices and into shelters, schools and job sites. People grieve differently. Some want to talk, others need to work quietly, many need both. Hotlines, peer support and drop-in counsellors make help feel ordinary. In the months ahead, special attention goes to first responders and volunteers who carry images and stories home long after the cameras move on. Housing determines whether a community scatters or holds. Rapid assessments tag what can be repaired quickly and what must come down. Programs fund shelter-in-place repairs, tarps, windows, doors, so families can return to a familiar street even if the living room is a construction zone. For those who can't return, interim villages of small, durable units go up on higher ground, with schools and clinics attached so they are communities, not camps. Rental vouchers and host family stipends widen options. The best programs keep people close to work, school and social networks. Distance is a second disaster. Every rebuild decision is a fork, restore as was, or change for the better. The honest rule is to rebuild fast where speed saves livelihoods, and rebuild smart where delay prevents future loss. Fast, main streets, clinics, warehouses and transit lines get quick repairs and safety checks. Smart, substations move inland or upstairs. Pump rooms that flooded get sealed and elevated controls. Windows in public buildings get shatter film, schools add sheltered interior rooms, water plants add extra days of treatment chemicals and backup generator hookups. Where streets are dug up for pipe repairs, crews lay conduit for future fibre. Where parks are redesigned, they double as flood basins with gentle slopes that can safely hold water during the next surge. If the crater or impact footprint remains, the land around it can be set aside as a memorial park and research area, a place that honours loss, supports science, and keeps people out of a zone that will always be unstable. The lessons for planetary defence are harvested with equal care. If 3i Atlas caught us with short warning, the argument for more eyes on the sky is no longer abstract. Funding flows to all sky surveys, southern hemisphere coverage, and space-based infrared telescopes that see dark objects against the sun's glare. Data pipelines are hardened so new detections can be verified and shared globally in minutes, not hours. On the mission side, agencies agree to keep a few interceptor spacecraft in a warm state, stored, tested, and ready to be adapted, so we aren't designing from scratch with the clock running. International playbooks for decision-making are clarified: who calls what, who authorises which actions, and how to coordinate without red tape when time is short. Treaties are revisited to allow a controlled standoff burst in space if that's the best way to save lives, with strict verification and debris mitigation baked in. Science gets a rare, harsh gift: samples and signals from a traveller between stars. Teams collect microtectites from rooftops, drill cores from the crater's edge, and trawl fine spherules from lake bottoms where ash settled quietly. Spectrometers read the chemistry of dust caught on filters, and ice cores retain a thin line that future students will hold up and say, "Here, this was the year the sky went strange." Those samples recalibrate models of how often interstellar visitors arrive, how they hold together, and how they break. They also feed dreams, how materials form around other stars, how organics travel between systems. Out of wreckage, knowledge grows. Culture stitches itself back together through ritual and routine. Anniversaries are marked with candlelight walks, bell rings, and the planting of trees. Art appears on plywood and later on walls, murals of the bright flash, the dark wave, and the hands that lifted people out. Museums curate exhibits that document not just the pain, but the response. The maps, the radio scripts, the boat lists, the homemade tools. Schools fold the story into local history so the next generation knows why the seawall has a break that looks like a beach, why the substation is now a garden, why the sirens are tested on the first Wednesday. Remembering becomes a form of protection. Economies creep from shock to rearrangement. Some businesses never return, others are reborn in new locations or forms. Entrepreneurs spot gaps, mobile clinics, modular construction, local repair co-ops, and fill them. Training programs pivot people into the trades most needed for years: electricians, welders, operators, nurses, surveyors, GIS techs. Insurance and reinsurance markets reprice risk. Governments backstop where needed, but also steer rebuilding with carrots and strings attached to safer siting and stronger codes. Ports dredge new channels and add all-weather berths. Airports add rapid inspection teams and standby generators. Railroads replace vulnerable signal huts with elevated shelters. Over a longer arc, the atmosphere's veil thins, and the planet's rhythms drift back toward familiar. If 3i Atlas was small to mid-sized, the cool summers and strange sunsets fade within a year or two. Farmers, having experimented under grey light, keep some of the hardier varieties in their seed mixes. Utilities keep a wider fuel portfolio to ride out solar dips if haze ever returns. Emergency managers keep a permanent stock of air filters, eye wash and glass film because they prove their value. The world has a new baseline of readiness that pays off for storms, fires and quakes as much as for skyfall. Policy follows memory. Cities update land use maps. No rebuilds in the inner run-up zones. incentives for living above the second floor in the most exposed districts, buyouts where the calculus is cruel. Regions formalise mutual aid compacts that worked well and discard those that did not. Nations run joint exercises that assume an interstellar object on a tight clock, so the next alert doesn't feel like first contact with the concept. Space agencies publish after-action reports that do not hide the misses and near misses. Transparent accounting of what failed and what saved lives becomes its own kind of monument. For individuals, the lesson settles into habits rather than fear. A go-bag in the hall. A family plan that includes auntie on the other side of town. A reflex at a bright flash. Look away, get low, count, cover. A sense of place that knows which street goes uphill fastest, which building has an interior hall with no windows, which neighbour needs a knock if the sirens sound. Communities that share those simple habits are not fragile, they are supple. If there is a gift in a hard season, it's clarity. 3i Atlas forces the question of what we value and what we'll change to protect it. The answers are surprisingly practical. See the sky better and sooner. Keep a small fleet ready to fly. Build neighbourhoods that bend without breaking. Store a little more grain and a little more grace. Teach children the handful of moves that turn panic into poise. Honour the lost by choosing the safer line on the new map. And keep telling the story, not to tremble under it, but to stand on it, so that the next time a stranger from between the stars slips into our sky, the world meets it with practiced hands and a plan. If you've stayed with me to this final moment, take one slow breath and look up, really look up, and remember that we live on a world flying through a living sky. Tonight, the stars will seem very far away and very close at the same time. We've walked through the first blinding flash, the rolling shock, the long shadow in the atmosphere, and the chain of choices that follow. We've seen how a stranger from between the stars, 3i Atlas, could turn a quiet morning into a page that splits history into a before and an after. And we've seen something else, that our future is not a spectator sport. It's a team project stitched together by foresight, practice, and the courage to act when the clock runs loud. Hold on to the simple truths. Time is everything. See earlier, decide faster, move wisely. A handful of habits. Look away from the flash, shelter from glass, go uphill near the coast, listen for the next official update, can turn confusion into survival. A handful of investments, wider sky surveys, ready-to-fly interceptors, resilient grids, living shorelines, can turn catastrophe into a hard chapter rather than a final one. We don't need to be perfect. We need to be prepared. If 3i Atlas ever comes calling, the headline won't only be about rock and fire, it will be about people. The nurse who keeps the generator humming at a clinic, the radio volunteer who passes a message when the phones go dark, the kid who remembers the evacuation route and tugs a neighbour in the right direction, the pilot who climbs for smooth air, the mayor who speaks clearly and tells the truth even when the map still has question marks. Disasters reveal physics, responses reveal character, and character is something we can choose and practice long before the sky turns strange. There's another thread to pull, and it's older than fear. Wonder. Interstellar visitors are not just threats. They are messengers of distant birthplaces and alien winters, fragments of worlds that formed under another sun. If one ever crossed our path and missed us, we'd chase it with telescopes and probes, trying to read its chemistry like a letter. If one came too close, we'd still learn. In the hardest way, yes, but learn we would. About the strength of stone and ice forged far from home. About how our atmosphere wrestles with a starshot intruder. About how societies bend and don't break when the unexpected arrives. Awe and caution can live in the same heart. So as the credits roll on this thought experiment, ask yourself what part of the plan you own. Maybe it's as small as putting a flashlight, a radio, and copies of documents in a drawer. Maybe it's talking to your kids about why we don't stand at windows when a brilliant light blooms. Maybe it's showing up at a community drill, or voting for the kind of city that moves substations out of floodplains and puts trees back on dunes. Maybe it's nudging your curiosity toward the night sky, following the surveys, cheering the engineers, supporting the science that keeps watch while we sleep. If this video sparked something, share it. The more minds that know the basics, the fewer hearts that panic when the sirens sound. Drop your thoughts below. What would you add to the playbook? What did we miss? What do you want explored next? And if you want more deep dives into the fragile, resilient dance between humanity and the cosmos, subscribe and stay close. We make these journeys together. One last picture to carry with you. A quiet street, late after the power comes back. A window glows. Someone makes tea. Someone else checks on an elderly neighbour. A small radio hisses with a calm voice giving the next day's plan. Overhead, the sky has started to clear. The same stars are there. The same river of night. The same distant suns that send us rare travellers like 3i Atlas. We are small beneath them, yes, but not helpless. We know how to learn, how to prepare, how to care for each other, and that, more than anything a rock can do, is what will decide how our story continues. Thank you for watching. Stay curious, stay ready, and I'll see you in the next one.